app is slow, people love saying, it's the network. But what does that even mean? DNS, TCP backlog, packet drops, slow TLS handshake, wrong route, MTU, socket exhaustion, retransmits. In this video, we'll make Linux network debugging feel structured, visual, and practical. Let's place networking in the Linux stack. At the top, the application uses socket APIs. It may call socket, connect, accept, send, ref, poll, select, or ethtool_wait. The kernel then handles socket state, routing, queues, buffering, retransmissions, and NIC interaction. Below that, the network interface card and physical or virtual network path carry packets outward. So Linux networking sits at the boundary between application I/O, kernel packet processing, and the actual network path. Network commands help you observe different parts of this stack. Use this four-step mental model. 1. Can I resolve the name? 2. Can I open the connection? 3. Can packets flow cleanly? 4. Can the application consume and respond in time? Think of DNS as the phone book. Connect is dialing. Packets are letters on the road. Application response is the person actually answering and speaking. Linux network commands fall into families: identity and path, IP, IP route, IP address, IPNA, name resolution, dig, resolvectl, host, socket state, SS path quality, ping, MTR, traceroute, packet visibility, tcpdump, interface health, ethtool, IP-S link, throughput and saturation context, SAR-N, SS-S, app metrics, cloud metrics. DNS tells you what number to call. Routing tells you which road the packet will take. The neighbor table tells you who the next hop MAC or neighbor is. Use dig or resolvectl to check resolution time. Healthy, query time a few milliseconds. Issue, query time hundreds of milliseconds. Use IP route and IP route get to see the path. Healthy, via your gateway. deveth0, src your address. Issue, network is unreachable. Use IPNA to see the neighbor table. Healthy, reachable with a MAC address. Issue failed. DNS is the phone book. Route is the GPS. The neighbor table is who do I hand this packet to next. Sockets are where apps actually talk. SS-S gives a summary. SS-tanp shows TCP states and owning processes. SS-ltnp shows listening sockets. Healthy, a few hundred established, some time wait. Issue, tens of thousands established, hundreds of thousands time wait, or many syn or close wait. Syn means dialing but the call is not connected. Established means active call. Time wait means waiting briefly after close. Close wait means the remote closed, but the local app has not finished cleanup. Huge time wait may mean churn or poor connection reuse. Many syn may mean path, firewall, or downstream issue. Many close wait may mean an app bug. Ping is basic round-trip time and reachability. MTR shows latency and loss across hops over time. Traceroute is path discovery. tcpdump is ground truth on packets. Healthy ping, RTT min average max under a few milliseconds, no loss. Issue, high latency, 20% loss or more. Healthy MTR, zero loss, low average latency. Issue: 15% loss, high average. Healthy dump. Normal SYN, SYN ACK, no repeated retransmits. Issue: mini TCP retransmission or ICMP frag needed for MTU. Retransmit is like resending a letter because the first one never arrived. Jitter is commute time, changing wildly every day. IP-S link shows packet and byte counters, errors, and drops. ethtool-S gives deeper NIC driver stats. SAR-N shows throughput and TCP retrans and error counters over time. Healthy, RX and TX error 0, dropped 0. Issue: errors and drops in the hundreds or thousands. ethtool healthy, RX underscore dropped 0, TX underscore amount 0. Issue: RX underscore dropped high, TX underscore amount non-zero. NIC stats are dashboard warning lights. Drops are like mail thrown away before delivery. Now zoom into the syscall path. An app may call socket, then connect, then send or rec, then poll or epl underscore wait, then close. If connect is slow, maybe DNS, route, firewall, or the SYN path is the problem. If poll waits too long, maybe the remote side is slow or packets are delayed. If rec blocks, maybe the app is waiting on the network, or maybe the app is waiting on the app. Use trace-tt-t-p and the process ID for a short sample. Healthy, connect returns in a few milliseconds, rec in under a millisecond. Issue: connect takes over a second, poll blocks for seconds, rec slow. Syscalls reveal where user space time is going. Not all network delay is wire delay. Same Linux tools, different surrounding realities. On EC2, virtual NC and ENA behavior, instance network ceilings and PPS limits, VPC flow logs and reachability analyzer as supporting tools, CloudWatch correlation for network performance. You cannot inspect the AWS fabric directly, but you can inspect Linux symptoms and AWS metrics. In the data center, real switch and NIC faults, cable and transceiver issues, driver and firmware mismatch, switch port errors. Physical faults are more directly yours to check. Scenario A: slow app before the first packet. DNS lookup slow. Use dig or resolvectl. Scenario B: service reachable sometimes, then times out. SYN sent, path issue, firewall, or target overload. Use SS, MTR, tcpdump. Scenario C: high CPU blamed on the app, but actually connection churn. Huge time wait, poor keep alive or reuse. Use SS-S, SS-tanp. Scenario D: MTU mismatch. Path works for small packets, breaks for larger or TLS flows. Like a sofa through a too small door. Use ping with size and DF, tcpdump, MTR. Scenario E: NIC errors on bare metal. IP-S link, ethtool-S. Scenario F: EC2 network ceiling or ENA-related symptoms. Linux looks mostly normal except latency under burst. Correlate with AWS metrics. Here's the mental model. Use DNS commands to confirm the name. Use IP route and IPNA to confirm the path. Use SS to see what the application is actually doing. Use ping, MTR, traceroute, and tcpdump to inspect packet behavior. Use IP-.